This is section 1.2b, graphs of equations. Today we're going to talk about symmetry, the different kinds of symmetry. First, y-axis symmetry. In graphs that have y-axis symmetry, the points xy and negative xy both satisfy the equation. And here we have a sample graph that satisfies xy and negative xy, or y-axis symmetry. Okay, so this is a parabola, x squared minus 2, and we see it has that familiar shape of the parabola. And the reason this is called y-axis symmetry is that it's as if the y-axis is a mirror. Okay, think of the y-axis as a mirror, and you could also think of it as an axis around which you rotate a curve. Okay, so like if you think of it as a mirror, well, whatever is on the right side of the mirror is reflected on the left side of the mirror. Or if you think of it as an axis of rotation, well, what you could do is just pretend that there's only half of the graph, and then you swing it around 180 degrees to the other side, and you get something that looks like a parabola. Okay, so any way you want to think of it is fine, as long as you remember that y-axis symmetry means that a graph is symmetric about the y-axis, or that the y-axis acts as a mirror for the graph. Alright, and the specific points that are given here to illustrate y-axis symmetry are the points -3, 7, 3, 7, -2, 2, and the other point 2, 2, and then -1, -1, and the point 1, -1. These pairs were chosen because they show you that if we have a point 3, 7 on a symmetric graph like this, a graph that's symmetric about the y-axis, well, then we're going to have the point -3, 7. They're only going to differ in sign in their x-coordinate, whereas their y-coordinates will be exactly the same. This is also true down here, what I'm circling now with the mouse arrow. Alright, that pair of points is -2, 2, and 2, 2. Alright, and they only differ in the sign of their x-coordinate. Alright, so visually we can see that y-axis symmetry means that the y-axis acts like a mirror, but algebraically y-axis symmetry means that the point xy and negative xy are both on the same graph. Now let's talk about x-axis symmetry. X-axis symmetry. With x-axis symmetry, the x-axis is acting as the mirror. Okay, the x-axis is acting as the mirror. In graphs that have x-axis symmetry, the points xy and x negative y both satisfy the equation. Alright, so we look at these points here. I've got the points 3, 3, 3, -3. They only differ in the sign of their y-coordinate. Alright, because the x-coordinates are the same, and that is algebraically what x-axis symmetry means. Visually, the x-axis is acting as a mirror. Algebraically, xy and x negative y are both on the same graph. And this specific graph is for the curve x equals 2/3 y squared minus 3. And x equals 2/3 y squared minus 3 is you can think of that as a sideways parabola, a parabola that faces right. Origin symmetry. Alright, in graphs that have origin symmetry, the points xy and x negative y both satisfy the equation. Alright, so you can think of this as a symmetry, a symmetry that's diagonal, if you want to think of it that way. Or you can think of it as a symmetry that's flipped or rotated clockwise until you get 2 quadrants away. Whatever you want, whatever way that you come up with for remembering this symmetry is fine. As long as you remember that whatever's in the first quadrant is reflected and inverted in the third quadrant. And then also, whatever is in the second quadrant is reflected and inverted in the fourth quadrant. All right, that's all you have to remember with this kind of symmetry. Or if you want to just think of it as the symmetry that passes through the origin, that's fine too. In any case, if the points x, y, and x, y are both on the graph, then we have origin symmetry. And here the sample points are 5, 3, and -5, -3. See how they differ in the sign of both coordinates. They differ in the sign of both coordinates. And this is for the cubic equation x equals 5/27 y cubed. X equals 5/27 y cubed. All right, that's a cubic equation, and that is symmetric about the origin. Symmetric about the origin. Some examples. What kind of symmetry does y equals 1/2 x squared plus 3 have? All right, you're going to do this on your own, but just a little hint about how to proceed. You need to do some tests, okay? You need to try -x and keep y the same and see if you still get the same equation. Or you need to try -y and keep x the same and see if you get the same equation. Or you have to try -x and -y and see what happens. Right? Those are the tests of symmetry. Those are the tests of symmetry. So do those tests and see if you can figure out what kind of symmetry this graph has. So pause the video, do that, and then resume when you have an answer. Y equals 1/2 -x squared plus 3 is the same as y equals 1/2 x squared plus 3. All right, so what do we do here? You can see I've got this -x because that was just how I was testing. You need to try sometimes several different options. In this case, probably the first thing you thought of trying was to plug a -x in and see just to see what would happen. And sure enough, if I plug -x in to this equation, well, the negative becomes a positive because -x times -x is simply x squared. And so if I plug in -x, I end up with the same thing I started with, which was y equals 1/2 x squared plus 3. And so this is y-axis symmetry. All right, with y-axis symmetry, the points xy and -xy are on the same graph. And I've proven that algebraically because it turns out that -x and x both give me the same y value. -x and x both give me the same y value. Therefore, this is y-axis symmetry. What kind of symmetry does x minus y squared equals 1 have? All right, so pause the video, do that on your own, and then resume when you have an answer. Well, x minus -y squared equals 1 is the same as x minus y squared equals 1. And this is similar to what we did in the last example. And that's because -y times itself, what I'm circling now is the term -y squared. -y times itself is just positive y squared. And so we end up with the same thing. X minus -y squared equals 1 is the same as x minus y squared equals 1. Therefore, this is x-axis symmetry because you see, whether I put y or -y in, I end up with the same x-coordinate. I end up with the same x-coordinate. Therefore, this is x-axis symmetry. What kind of symmetry does y equals x cubed minus 4x have? All right, pause the video, do this one on your own, and then resume when you have an answer. Well, -y equals -x cubed minus 4 times -x is the same as y equals x cubed minus 4x. All right, let's make sure we understand why this is true. All right, so if I have -y here, you see all I'm doing here is testing, and I'm replacing xy with -x, -y, to see if it turns out to be the same. All right, and algebraically, what I'm circling right now with my mouse arrow, the equation -y equals -x cubed minus 4 times -x, That is the same as y equals x cubed minus 4x. Now you can prove that to yourself by doing the math, and you'll see that here on the left you're going to end up with negative y equals negative x cubed plus 4x. And then you just multiply everything by negative 1 and you get y equals x cubed minus 4x. These equations are equivalent. Therefore, y equals x cubed minus 4x has origin symmetry. What kind of symmetry does y equals 1/2 times x minus 2 squared plus 1 have? Alright, so what you want to do is pause the video and do all three tests of symmetry. In one test, you're going to test for y-axis symmetry and see what happens when you plug in negative x and keeping y the same. The other test will be testing for x-axis symmetry, in which you see what happens when you plug in negative y and keep x the same. And finally, you're going to test for origin symmetry, in which you plug in negative x and negative y to see if algebraically you end up with the same equation. Alright, so do your three tests of symmetry, and then after you pause the video, do that, resume when you have an answer. This equation doesn't pass any of the tests for symmetry, so it has no symmetry. Now, you might have sketched this on your own, or you can do it on your calculator if you want, and you'll notice that you have a parabola. And parabolas, they all have, an axis that goes to their center, and they're symmetric about that axis. Every parabola is. And so sometimes students get confused because, that a parabola is a symmetric shape, and yet here we're saying that this parabola of y equals 1/2 x minus 2 squared plus 1, we're saying that that parabola has no symmetry. Alright, well, it doesn't have y-axis symmetry, x-axis symmetry, or origin symmetry. Therefore, by these terms, it has no symmetry, even though it does have its own kind of symmetry. Now, for the purpose of this chapter, we're going to say that if a curve, a graph, does not have y-axis, x-axis, or origin symmetry, if it has none of those three, then it has no symmetry. Last thing we'll talk about today is I'm going to talk about circles. By the distance formula, r equals x minus h squared plus y minus k squared. Alright, so right now we're simply proving the standard form of a circle using the distance formula. Okay, looking at this diagram that I'm circling right now with the mouse arrow. Alright, this is a classic circle, right? And the point xy is somewhere on the circle. The point hk is at the center. And r is the radius. Well, using the distance formula, this distance r is square root x minus h squared plus y minus k squared. Because I can consider x my x1 and h my x2, and I can consider y my y1 and k my y2. Alright, so the distance r is given by the distance formula, and I can see that that is r equals x minus h squared plus y minus k squared, and then I simply square both sides of that equation, and I end up with r squared equals x minus h squared plus y minus k squared. Alright, and that makes a lot of sense because this is my x and my y, and the h and k are the x and y coordinates of the center. So all we've done here is just briefly proven the standard form of a circle. Kind of like how we proved the standard forms of conics in chapter 10. X minus h squared plus y minus k squared equals r squared is called the standard form of a circle equation. And so here's the question. The point 3, 4 lies on a circle whose center is -1, 2. Write the standard form of this circle. Alright, now I'm not going to show you how to do this because at this point, especially after having done chapter 10, this problem should be pretty easy for you. So pause the video, use your givens to figure out how to write the standard form of the circle, and then resume when you have an answer, or if you get stuck. X plus 1 squared plus y minus 2 squared equals 20. That is the answer. Okay, and so you might wonder, well, how did you get that answer? And the simple way to get that answer is just plug in your points. Just plug in your points, because you know that the point 3, 4 lies in the circle, and therefore you can use 3 for x and 4 for y. You know that the center is hk, and so you use -1 for h and 2 for k. And there you've already filled in 4 variables, and you can use those 4 to find the radius. Alright, so just plugging in 3, 4 for x and y, and then -1, 2 for h and k will give you the radius. Alright, and when you find the square of that radius, you get 20. You get 20 because the radius is root 20. Alright, and root 20 squared is 20. So the way that I write the standard form of the circle is x minus h, and since h is -1, well, x minus -1 is x plus 1, and then I have y minus k, and since k is 2, I have y minus 2. So this is the standard form of the circle. Alright, the classwork, page 23, and please write these numbers down, and we'll see you in class.